Hello everyone, and welcome to our webinar on the digital transformation of the end-to-end service lifecycle. I'll just give you an idea of our agenda today. So what we're going to run through is an introduction to CAD-IT, an overview of our Fiat 500 project, the role of Industrial IoT, an overview of ADIA, our diagnostic system, and then a demo of the three core elements, which are IoT, Diagnostics, and Technical Publications. And then finally at the end, we'll do some questions. Who are CAD-IT? So CAD-IT are a privately held group. We have over 600 employees worldwide. Our headquarters is in Singapore, but we have over 20 offices worldwide as well, in all the different regions. We have amassed over 125 international awards, and we specialize in Industry 4.0, sort of namely design, simulation, manufacturing, SLM, PLM, and technical publication. And our ultimate aim is to provide world-class Industry 4.0 solutions and services to our customers. We work in a really broad depth of industries, and you can see them all here: aerospace, automotive, industrial equipment, heavy machinery, medical, marine, electric and autonomous, and agriculture. So we've got a really good team of people who are specialists in all those different industries, and that helps us to help our customers, basically. So an overview of what we do are our capabilities. So there's three main segments to our capabilities, which are Service Lifecycle Management, Industrial Internet of Things, or IoT, and then augmented reality. And in today's webinar, we're really going to cover just the Service Lifecycle Management and the Industrial Internet of Things. So we can get a little bit deeper into that now. So we'll give you an overview before we actually do the demo of what's in the demo and what we're going to talk about. So I'll hand over now to Andy, and he'll explain the IoT-enabled digital thread.
Thanks, Neil. Good afternoon, everyone. Okay, so for those that maybe aren't fully aware of the terminology being used here, so IoT, the Internet of Things, or Industrial IoT, is effectively about connecting assets to the internet and automating machinery and assets within industry to gain efficiencies from those assets and gain insights into the data that those assets can produce. Now, when we refer to the digital thread, this is about the ability to connect the engineering product or the definition of that product. So this could be within your CAD models, your definition there, and flow that information down through the other life cycle processes. So this is the production of the product in the factory, or even if it's a product you send out into the field, it's the product as it operates within the field. So that could be the actual product you make within your factory that then has to operate in a car or on an aeroplane, or it could be a piece of machinery that you provide that has to operate on land or in another factory somewhere in the world. And what you can see there really is the example of the digital thread being more of a closed loop life cycle. So when the data is collected in the field, that information can be used to provide remote diagnostics and health information of the product so that you can predict whether that product is likely to fail and therefore act when it's necessary to prevent failure and prevent the cost of that failure when the product's in the field. And then really start to use that data to optimize how the product operates. So if that's a vehicle, you could have the data about how the vehicle operates to everything around it, the information about how that vehicle operates amongst other vehicles in the network and the distance that vehicle is to other vehicles in the network, etc. But as that data starts to flow back about the performance of that vehicle or that asset in the field, you can start to use that to understand whether the vehicle build process has impacted the life of the product. So you can update and improve your manufacturing processes. and then flow that real world data back into your engineering models so you can use that for the simulation of the design of the product in future. So you can really improve product based upon the real world values of how that product operated within the field. So you can really see how the two worlds of sort of PLM and SLM come together with the data that can be captured and generated by IoT, but also leveraging that efficiency from the connected product, so you can remotely access that information and remotely influence the product as it's out there operating in the field. So moving on from the digital thread, what we really see there then is this is a foundation for the digital twins. So in the case of a factory, the digital twin is about allowing you to use the data that you collect using the IoT capabilities to predict when a machine needs to be maintained, rather than having maybe planned maintenance schedules when it's not needed, so only maintain it when it's required, or predict when a product could fail and act accordingly. Really benchmark the assets because of all of that real life performance data that you get from your factory, and validate those machines with precise simulations to really understand how that real world data impacts how the machine really performs. So you're really leveraging that performance data back into your factory twin model to understand how that data affects how your factory operates. And that's very similar from a product perspective. So you can flow the data back into your design product to improve those designs, iterate the product designs in response to the performance data, and really reduce the prototyping effort, which would maybe normally require many iterations before you get it right. Okay, moving on now.
Okay, so let me just introduce you to ADIA, which is our interactive guided diagnostic system. So ADIA consists of there's four things that make ADIA quite unique. First being its integration with IoT. So that sort of facilitates remote diagnostics to prevent customers having to come to a dealer to actually get their vehicle or their product diagnosed. Provides an insight into the fault history to aid the diagnostic process, and it facilitates fault fix condition monitoring, which is really beneficial to OEMs as well. The second part is artificial intelligence. So we use artificial intelligence in both the search function to help the technicians find what they're looking for quicker, but also on the solution relevance. So if something is more of a fault trend recently, then it will be bumped up the list, and the technician will be provided with the diagnostics for that potential solution instead of one that used to be possibly popular, and that ultimately helps the technician get to the root cause much quicker. The next thing is integrated data analysis, and that just allows OEMs to configure their own dashboard, and be able to analyze what's going on in the field with their products, with their vehicles, to see what the most common fault trends are and what's emerging. So that sort of enables the OEM to jump on these problems a lot quicker, rather than them spiraling out of control and you only catch it in the warranty data, you know. So, and then the final feature that we've added is a technical support function, and that just really allows technicians to contact the OEM directly for technical help if it's not available within the system. And then once that fault has been corrected, again, they can send the information to the OEM and they can put it into the system so that you don't always have to contact technical support. So that's a little bit of an overview of ADIA, and we'll show you a demo of it in a few minutes. So this slide's really just an overview of our end-to-end process, and we'll bring this slide up after the demo as well, just so I can explain what we've just shown you. So it starts off with your IoT, your connected car, and that's integrated with our AI diagnostics, which then links out to our technical publications portal, where we've got all of our technical publications that are product specific as well. So you're not constantly having to enter vehicle details or user details. It's all one continuous thread. Then we sort of do a fault verification using IoT as well, and sort of remote condition monitoring. And then finally, we'll talk a little bit about service lifecycle management and SBomb management, and how we feed the information from the previous steps into our SBomb management so that we have a more reliable product at the end. So what we'll do now is we'll move on to our demo. I think we've talked about it enough, but we're going to start with IoT, move into diagnostics, and then finish with technical publications. So I'll hand back over to Andy now, and he can demonstrate the IoT. Just a point of note here, we've recorded all of these videos, and we're going to talk through them. And the reason we've done that is just because we're all in different locations today, but we are doing a live demonstration on our actual physical Fiat 500 in April, and we'd love as many people to join and be there in person to see the technology working. So I'll start it off. Over to you, Andy.
Thanks, Neil. Okay, so this first part really is just to introduce to you how the car is actually connected to the internet. So you can see there from the diagram, hopefully, we have a OBD2 connector in the car. So there is a piece of hardware, we can call a gateway here, that is on one point connected to the internet, but also has a connection through an OBD2 cable into the car. Now on that hardware is some software, and that software has been written to be able to read the values from the vehicle, do some computation with those values, and send the information up to MindSphere. So you can see you'll be able to see the information flow into the IoT platform, and then those values can be viewed. Now, what you're seeing now on the dashboard is how many assets are connected, how many dashboards are connected, and how many rules are configured. So this is a landing page that's available as soon as you enter the IoT platform to see how many vehicles in this example are connected, and then how many different insights have you set up with dashboards, and how many rules have you set up to detect if a particular value, such as a sensor or a temperature, is going outside of range. And then those rules that have been pre-set up can then trigger events, and those events would be presented on this landing page as errors, and you'll see that as part of this demonstration. And when those errors are triggered, you can then see whether somebody's acknowledged those events, and then you can see whether those events have created an email. When in this example the service center sees that there's an event being triggered, so a car is running and it's created a fault, that event will send an email to your inbox, or it could also be a push notification to your mobile phone. So what you'll see in a second is that email arrive, which you can see on screen. And that email gives you the details of the particular event that's occurred, which vehicle, and the description of the particular fault and the severity of that fault. So it could be just some information, some warning, but in this case, it's an actual error. So then we can look at this information in many views. So the technician, the service center or the technician can go straight into the event from the email, see where that vehicle is located. You can see here now very quickly what event's been triggered, and then start to kick off a series of procedures to create a work order for somebody to investigate the fault. So now you can see this work order is being created. So this is like a ticket that the service center can assign to a technician or a technical center supervisor to then assign that to another technician within their team. So they're selecting which asset automatically, where that fault's come from, and the priority of that particular incident. They can add some attachments if they wanted to support the ticket that's been raised. But as soon as that ticket has been raised, that will also trigger a notification to the person that it's been assigned to. So it's very similar to the fault that was triggered earlier directly from the vehicle, where an email was sent to an inbox. In this case, the work order sends an email directly to the assigned technician to pick up that particular ticket. So you'll see there the work order has now been received, also in my inbox. And now I can go from that work order. So this would potentially be a different person and will also be directed directly to the information that was generated for that work order. So I can see all of the information that was entered at the time of the ticket being raised. And now I can go and investigate that particular vehicle. So you can see there the status of the fault. I'll now change that to in progress. I'm going to go and do some investigation. So within the application itself, there's a few more tools that I can use to carry out that investigation. So as I head into the landing page, I can see very clearly that there's been the O2 sensor fault raised a couple of times. There's been 2 events triggered. So I can go to that particular value and do some analysis. So I'm now on the data that's been received from that vehicle. I can look at the O2 sensor values. I can see the change in that value over time. I can then look at a specific dashboard that's been designed to monitor the vehicle. And these can be custom dashboards designed by specific technicians or teams. And I can see on that dashboard exactly which sensor on the vehicle and where has been triggered and what fault has been raised. Now that fault is a fault code. I can see that the sensor voltage is too low and there's a P0137 fault. Now, this allows me to pass that information onto the diagnostics platform, and it will allow the technician to link straight through to the diagnostics procedure that is appropriate for diagnosing that particular fault. So from this point, I think, Neil, you're going to pick this up from here?
Yeah. So, okay, we'll play this. So, essentially, as Andy said, we've got our O2 sensor fault and it's flashing red on here. And in order to launch that fault code into our diagnostics platform, you can simply click on the flashing light. That'll launch the ADIA, which is our interactive guided diagnostic system. And it uses AI-based reasoning to guide technicians to the fault as quickly as possible. And as we mentioned earlier, there's an integrated support function as well. So essentially, when the technician lands here, they'll be presented with a sort of a list of questions, which are sort of ordered in order of what's most relevant to do. So in this instance, it's asking them to look at the IoT dashboard and check if the sensor voltage is correct. Now, we already know that it's not correct, and what they're going to have to do is just answer the question here. So in this case, they're going to click no, ask is within the expected range. So once the video catches up, they'll click no, and it'll move on to the next question, which is do a check of the O2 sensor wiring for any damage or corrosion. And we're just displaying a mock-up of that wiring harness where exactly they need to check. So they'll click no because they haven't found any damage to that. The next one is to do an inspection of the exhaust system for any leaks. In this case, the technician does find a leak after inspecting it. So we'll drill down a little bit further into this, and it's asking, where is the leak? Is it at the manifold gasket or is it at the catalytic converter? So in this case, it's the manifold gasket which is leaking. So it's this is the possible root cause. So we go to the solution then, and the solution will just present the technician with what to do next. And I think it's replace the manifold gasket. It also provides them with a link or a URL which will take them directly into the parts catalog, which is all VIN specific. So all the information has been passed from IOT Dashboard and into ADIA, and then ADIA passes it into our portal. And here we can see the interactive parts catalog. We've got the manifold gasket, which you can select from the 3D model, or you can select it from the list on the right-hand side. In this case, the technician clicks the shopping cart and orders that manifold gasket. So hopefully that will be delivered in the next few days. And the technician can either get on with taking out the old one. So we'll go into our interactive workshop manual, our 3D workshop manual, and it'll take them directly to the procedure for removing the manifold gasket. And as you can see here, we've got all the relevant cautions and warnings related to replacing an exhaust component. So once we get all of those out of the way and click that we're not going to hurt ourselves, etc., we can see that our animation starts to play. What it's doing now is just showing how to remove the rest of the exhaust. And on the left-hand side, you can see there's text steps as well. So if someone wants to pause it and just read the detail of the text, if they can't understand what's happening in the animation, they can do that as well. So here we can see they're just about to take the manifold off and access the gasket. And then it'll just show a reversal of the same procedure in order to put it all back together. So once the technician's fitted everything back together and he's happy with the work, they'll then go and consult the IoT dashboard again in order to verify that that has actually fixed the problem. So I'll hand back over to Andy and he can explain how they would do that.
Thanks, Neil. So you can see now that the technician's got access to the dashboard. They can still see the values on the vehicle. Now, what's important here is that for this particular vehicle to be determined as fit and healthy and roadworthy, it needs to be tested. So you can see when a test occurs, the values are live and automatic, and they're captured. They'll be able to see live on the dashboard those values change, and that the sensor now is showing a value that's within range. So that shows that the vehicle, the sensor value is accurate and acceptable. So now they can see the original errors, and it's necessary to acknowledge these to confirm that actually something's been done about it. But the system will also be checking that the values that are present within the database are within the specified range. Otherwise, the vehicle wouldn't be classed as healthy, and there would still be a sort of red indicator against it. But you can see now the error is clear. The work order that was in progress can now be updated to done. And now we can go back into the landing page and see that all events, all errors, and all work orders have now been cleared.
Awesome. Thanks, Andy.
Okay.
So finally, we can talk a little bit about SBomb management, and our colleague Kute is going to take us through that. So play on this.
Thanks, Neil. So we have now finished the demonstration on the vehicle, and now what we would like to show you now is actually how we create or update that content that's is displayed within the portal. So we are going to start with creating the initial parts, or the part which failed, and we are going to show you the demonstration within the Team Center and the RapidAuthor, which are connected or integrated together. So, and I will also explain a little bit more about the integration when we go into the update process. So yeah, now we are just going to complete this procedure within RapidCatalog. And as I mentioned before, so this would have been the initial parts that we created, or the parts which failed. And then we will go into Team Center to initiate the updates, which would be the bringing the new part in, or which would be like the replace the old part widths. Okay, so now we are going to save this back to Team Center. So now that procedure has been saved back in Teamcenter. So because of the content that we have created is directly connected to the original engineering CAD data, when a change happens to that data, we are not notified about that because our part is associated with it when a change happens. So, and also like because of we have a part in our publication that has changed. So now we are going to show you that change process and then the updates. So now we can show we have gone from the standard parts to the revised parts, which shows the change that has happened. And after this step, so we have to go into the RapidCatalog and update the process that we have already created. And we are running the import and update process. And thereby the changes have been recognized by the software again within the Teamcenter. Now the job has been successfully done. Yeah, and now we have done the update within the Teamcenter. And we now need to open the RapidAuthor to view and accept the changes within this update. And we switch back to RapidAuthor, RapidCatalog directly. So what's really important to understand here is that so not only the publications we create associated with the engineering CAD, as mentioned, the strength of the change management, but also the speed of what we can update is very fast and efficient. So all the changes are displayed in the lists, which we can view one by one. So you can see on the screen, we have a before and after parts, which are the new and the old versions. And what's great about using the CAD and RapidAuthor is here actually the simplicity and the speed which you can carry out this procedure. And in traditional technical publications, this is lengthy and non-connected, or I would say like non-integrated. And now we are going to save back this project back in Teamcenter after the change. And the changes are transmitted back to our PLM system Teamcenter. And it's all like the automatic process, which you don't need any extra or additional import or exports. And now job is completed. So we went through the creating an initial page of the parts catalog, and there has been a change in the engineering data. And because the part is associated with our publication, we are notified about that. And we can go into a check and validate the updates with a really little effort and republish it within a very short time frame. Yeah, you can.
Awesome. Thanks, CADIT. So just to summarize what we've just taken you, so we've just taken you through our integrated approach to fault identification, diagnosis, and correction. We're highlighting a solution which is designed to minimize downtime and maximize after sales revenue. So by using IoT to monitor the fleet for faults, the OEM is able to sort of proactively identify and prepare to rectify customer concerns, which saves both the OEM money and the customer money. The integration of IoT and guided diagnostic facilitates the seamless transfer of fault data sort of between the systems, and that sort of mitigates the risk of, you know, you're wasting time. Previously, you'd be wasting time trying to understand from a customer what potential fault could be, and there could be a lot of misinterpretation there, which again wastes time and causes the vehicle to be the vehicle or the product to be down for longer than it needs to be. Then by linking to our technical publications and their product-specific technical publications, that allows technicians to access the information that they need much quicker and much more efficiently. So they're not, sort of stumbling in the dark trying to find different documents. If they've got a link directly to the specific workshop manual procedure or the specific parts catalog that they need, that saves so much time. And then finally, by using RapidAuthor for the creation of and management of technical publications, OEMs can reduce or can reuse the CAD data, the design CAD data, to lower the cost of authoring and publishing content. And additionally, the content can be easily updated in response to engineering changes, and that's what Kute sort of was just demonstrating. That once we identify that there's a fault trend emerging, and in this case it was the manifold gasket, engineering can jump straight on that from the feedback we're getting from our IoT platform and our diagnostics platform. They can make the change to the design, and then because our publications are integrated with the CAD data, then there'll be a notification that comes through to the publications team, and they can just simply update the procedure very quickly. And we kind of estimate that having this integrated approach saves between 40 and 60% of authoring time, because normally engineering might make a change and it could be weeks before the publications team are notified, and in that time you've got a period of time where publications don't actually match the parts that are being sent out to your dealerships or to your service locations. So that's really an overview of what we've shown you and why we take this approach, sort of an integrated end-to-end approach to the service lifecycle. So I hope that makes sense to you, and we'll move on to some questions now. And if something doesn't make sense, then you can ask us now. So we'll give a few minutes. I know Alison's going to read out the questions coming in. Have we got anything, Alison?
I'll just give him another minute.
Okay.
Okay, so the first question is, how would you collect the data if it was a robot or CNC machine instead of a car?
Yes, okay, I'll take that, Alison. So as I described for the connectivity on the car, there's a piece of hardware there that's we call a gateway. Now that hardware has some software on it that's acting as the agent between the data source, in this case the car, and the data receiver, the IoT platform. Now, if this is a robot or a CNC machine or other industrial equipment, the principle will be the same. There's hardware which acts as a secure gateway. So one side of that gateway, one network port of that gateway, accesses the internet and provides a secure connection to the internet. And the other side is the connectivity port for the asset, the robot or the machine. Now, the key piece in the middle is the software, which ultimately contains the specific communication protocol for that machine. So there's a range of protocols available that many machine tool providers are now sort of standardizing on. So you may have heard of things like OPC UA and Modbus TCP over IP and a range of others. Now, these protocols are effectively formats of the data that can be understood when the matching protocol is selected on the gateway device. So it's very quick to determine what protocol or what language the robot is speaking, and then configure the gateway device to speak the same language, so use the same protocol, and then read the data from the memory of the robot PLC or sensors or whichever data source is providing the data on that particular network. But the gateway will be the sort of the middleman between the asset at the edge and the cloud platform, which is the IoT platform. Okay.
Okay, and then the second question, I guess, is kind of carrying on from this one, which is, I noticed this is an automotive-based demo. Does the same principle apply to other industries?
Yep. So, well, it's a good question. We've set this demo all around our Fiat 500, and that's just purely so that we can drive the Fiat 500 to a customer, and we've sort of got a mobile demo, if you like. But yeah, the same principle applies to all industries that I talked about at the start. So aerospace, heavy machinery, manufacturing, all those different industries. The same principles apply. So yeah, that was a good question.
And if I may add to that, so that that could be a conveyor in a warehouse that has motors and obviously moving parts and sensors, and that conveyor could be sending information about those motors, the temperature, the vibration, and that analysis would allow alerts just the same as you saw for the O2 sensor to be triggered. That information be sent to a maintenance team, which could be off-site or somewhere else in the factory, and really just allow the fix of that conveyor to be much quicker, because the alert could be proactive, as in there's a detection that this motor could be failing because of the temperature and vibration. The cause of that failure, or potential cause of that failure, could be sent to the technicians to then receive the correct part information and the correct diagnostics and fix procedures, repair procedures, so that when the technician arrives to repair that particular product, they've got the part, they've got the information that they need, and they can make a fix much faster and avoid lots of unnecessary downtime. So it applies to a range of industrial equipment and different sort of maintenance and service scenarios.
Okay, and then the last question for now is it possible to use these systems or technology in isolation, or do they have to be integrated?
So yeah, I'll take that one again. Brilliant question. So we're showing all of these different technologies in our ideal, scenario where you integrate everything. But each individual technology, whether it be IoT, ADA, or the technical publications, are all things that our customers can have sort of as a pick and mix, or if they just want one of them, that's something that can work. We're just trying to demonstrate the ultimate goal of the service lifecycle and all the technologies that are needed along the way, and personally what we think is the best solution for the job. But yeah, you can absolutely have those technologies on their own in isolation.
That's all the questions for now.
Okay, great. Well, thank you all very much for joining today. And just to remind you, we're doing this demonstration live, so you'll actually get to meet us in person and see our little Fiat 500 all connected up, and actually watch it happen in person. So please do come and join. Alison, can you just remind me of the date? I know it's in April.
It's actually the 10th of May.
Oh, sorry, right. It's the 10th of May. Yeah, please come and join on the 10th of May. Great. Okay, thanks everyone.